depends on what I have connected to the circuit. So if, for example, there is nothing connected to the circuit, this is very easy to turn. If I have the light bulb, it's moderately easy. And if I connect it together, it's very hard to turn. The difference in these three situations is the resistance of the external circuit. Here the external circuit has essentially zero resistance. It's only the wires. Here we had infinite resistance. And here we had maybe about 10 ohms of resistance for that light bulb. All right? So as you know, the amount of resistance is going to influence the amount of current in the circuit. So we had more current when there was less resistance. Now let's examine the cause of this mechanical resistance to turning from the viewpoint of something you know about induced electromagnetic fields, and that is Lenz's law. Okay? Lenz's law tells us that an induced EMF gives rise to a current that opposes the original change in flux. All right, so let's see how that applies to our generator right here. All right. As I turn this, I'm producing a current, and that current is passing through the armature. All right. So we have a current that is being moved in a wire through this armature, through this magnetic field. The result of that is an induced EMF. That induced EMF will generate a current which actually opposes the current that I'm producing by turning it. All right? And the result of that opposition is to create a force on the armature which opposes the force which I'm applying to the crank. That appears in the form of a torque, which is called a counter torque. So there's a counter torque opposing the torque or the forward torque of my turning. All right? And that's going to be greater when there's more current in the external circuit. So that's greatest when there's no resistance in the circuit, or essentially zero resistance in the circuit, so that there's the greatest amount of current. And that resistance, that counter torque, is least when the resistance is infinite and there's no current in the outer circuit. We're going to be looking at the forces that you typically encounter in solving force problems. There are four of them. Those forces are weight, tension, friction, and normal. Every object has weight. The weight is due, in this particular case, for this brick, the weight of the brick is due to the earth pulling on it. And the nature of that force is that it is directed vertically downward and directly toward the center of the earth. Another kind of force is tension. And tension force you can think of as a springy force. Here you can see the spring coils get further apart. It's obvious that a force is being exerted here. The nature of the tension force is that it always acts along the line of the spring, or it could be a string or a wire, and it's always the same amount in each part of the medium. Bungee man over here experiences a tension force, and that tension force is along the line of the spring that is supporting him. So as I pull, you can see the spring coils get further apart. That's a sign that more force is being exerted to pull Bungee man back up again. For strings, there are tension forces. It's not so obvious that the string is stretching, but if you stretch it hard enough, you can actually feel it stretch. And if you've ever messed with fishing line or thread, you can certainly feel those stretching if you pull them hard enough. Now, third kind of force is friction. We're going to leave that one as a separate topic to discuss in another video. So that leaves us with the fourth force, the normal force. This is a name that we give to forces that are exerted by solid surfaces, such as this table. When I put the brick on the table, we say that the table pushes up on the brick and supports it, and we call that a normal force. The reason we call it normal is that we're using normal in a different sense than one usually encounters, and that is in the sense of being perpendicular. Normal is a mathematical term for perpendicular. So the normal force on the brick is exerted perpendicular to the brick. That means if we put the brick on a slanted surface, the force will no longer be directly upward. On this inclined plane, the force on the brick is off at an angle right here perpendicular to the plane. If I raise the plane all the way up to 90 degrees, At that point, there would be no more normal force exerted on it. There would be nothing pushing. If the brick were here and the plane were here, there would be nothing pushing on the brick this way. Normal forces can be a difficult concept to understand. Let's talk about it from two different points of view. First, from a theoretical point of view, we know that an object which is at rest has no net force acting on it. So the brick is at rest here. We say that the sum of all the forces acting on it is 0. Well, one of those forces we've already said is the weight, which points down. Well, if all the forces on it act up to 0, it means there must be a force acting up to balance the weight. And that is, in fact, what we call the normal force. Now, if you're not satisfied with the theoretical description, we'll try to do it in a little bit different way to try to actually explain what's going on with the surface. Because the table looks like it's doing nothing. How can something that's doing nothing exert a force? Well, one way to see this is, let's put a pad right there and put the object on the pad. Now, I don't know if you can tell, but the brick pushes down a little bit on the pad and actually compresses it. If you have enough weight, you can see the compression in the pad. The more weight, the more compression. It's sort of like a spring. Where you stretch more on a spring, you have more force required to do that. Let's put a lead brick. This brick is covered in tape, but it's very heavy, and you can see that it presses quite a bit. So the fact that the pad is pressed so much means that the pad is exerting quite a bit of force. The scales that you step on in a bathroom scale, for example, work the same way. The heavier you are, the more you compress a spring inside, and the larger the reading on the scale is. Now, what you need to think of is that this table is actually acting like a spring or a cushion in the same way. Well, not quite the same. It's a much stiffer cushion. Think of it, there are lots of little atoms in there, and those atoms, think of them as holding hands or as having very strong bonds between them. And those bonds, while they're very strong, they can be stretched. And if you put a heavy enough weight on them, well, actually, if you put any weight on them whatsoever, there will be a very small amount of displacement. You might think of it as a fireman's net, but it's stretched so tight that you can hardly see the stretch in the net when something lands on it. Same thing with the table here, except it's even stretched more tightly than that. Now, if we put enough weight on the table, we could see the amount of the compression in the table. You can probably imagine if we put an extremely heavy weight, like a safe, we could make the table buckle under that weight. Now, with an object called an optical lever, we can see extremely small displacements, so we don't have to put a safe on the table. We can just put a small force on it, and we can see the table actually deform or move in response to that. And that's what we'll do next. We'll move to the classroom in order to see the demonstration of the optical lever. This is a setup to magnify very small motions in objects. For example, we're going to actually be looking at the motions of this concrete supporting column. This column actually goes down into the basement of the building 4 stories below us. So it's very sturdy and very difficult to move. I have an aluminum bar here which is attached to the wall with this piece of clay. And the bar rests at the other end on just a steel block. Now, between the block and the bar, I'm going to put this pin. Now, to the pin is glued a mirror, just a small piece of a mirror, and that slips right in between the bar and the block. And because the needle is cylindrical, it rotates easily underneath it. What's going to happen is that as either the table moves or the supporting beam moves, that the needle is, those motions are going to be transmitted to the needle, which is going to move back and forth, and so the needle will move back and forth. Now, they're going to be very tiny. In order to detect them, we need to amplify them, and to do that, we're going to use a device called an optical lever. That just requires a beam of light that reflects off of the mirror and goes to a distant screen. For a beam of light, we're going to use this laser beam. So it reflects off the mirror surface right here, and then it reflects back this way, and about 5 meters on the other side of the room, there is a screen where we can see the beam. So I'm just going to hit the table real sharply like that, and you can see that this causes the table to actually vibrate because the beam bounces up and down on the screen. Actually, you can see it's bouncing a little bit all the time because there's always vibration in the building. Now, if I'll just push down on it, you can see that the beam goes down a long distance. So although you can't, if you look at the table, you can't see it moving, it obviously must be moving. And so it is responding to the force that I applied to it. It's exerting a normal force back up on me. Now I'm pushing directly on the column. And you can see that the beam is moving a small distance. It's not as much as before when I was pushing on the table, which has a lot more give to it. But it's certainly moving further than just its normal vibration. Now we're on the opposite side of the wall as before. The apparatus is on the other side of the column, which is right here. And so now I'm going to push on it from the opposite side. I'm just going to put my shoulder into it. So we've seen some examples of several types of forces that you will encounter in physics problems. One of them is the force of weight. Another is the tension force, which we see on springs and wires and strings. And a third one is the normal force, the force that surfaces exert perpendicular to objects. A fourth kind of force you will encounter is friction, and that will be the subject of another video clip. What you see here is our version of the State Fair ride, the Giant Swings. Now, this is by no means giant, but they do provide very high accelerations, much higher than the State Fair ride does. For passengers, we're going to use these green-blooded aliens from the planet Jupiter. Now, they're used to experiencing large accelerations because, after all, they come from Jupiter, where the gravitational field is much higher than the Earth. We'll put one passenger on each pan. And put them in motion just by turning the crank. And if you've ever ridden the State Fair ride or watched somebody else ride it, you know that when it spins, the chairs move outward, and the faster it spins, the farther they move. Now, what you're going to be doing is analyzing this situation. You're going to be determining the acceleration of the passengers in two different ways and comparing your results. One method is simply to use the formula of force centripetal acceleration that you've already learned, namely the square of the speed of the object divided by the radius of the path. So you'll need to measure the speed of the passenger and the radius of its path. Now for the radius, take the distance from, say, about the middle of the passenger to the axis of rotation. Now that has to be a perpendicular distance to the axis because the motion, the circular motion, is in a horizontal circle. Now, for the speed, you'll need to know how fast the passenger is going around or how long it takes it to go around once. In order to use that, you'll use a video analysis program that we'll talk about again later. The other method is to do a net force analysis. So with the passenger in this position, you'll identify the forces acting on the object. There are two of them. And write the net force equations and solve for the acceleration. Now again, when you set up your net force equations, be sure to pick one of your coordinate axes in the direction of the acceleration. And remember again that that direction is horizontal because the circular path is a horizontal circle. You'll be doing the analysis using a video analysis program and some video clips that we've already prepared. In order to get your accelerations in terms of meters per second squared, you'll need to be able to take the distance measurements in pixels that you get from the video program and convert those to meters. So to do that, I'm going to measure one distance that you can use to obtain your scale factor. The distance I'm going to measure is from the inside of one of these uprights to the inside of the other one. Okay, now I've positioned the meter stick. What you need to do is make a reading. I would say read from the inside surface of the pole there, and it's good enough to read to the nearest millimeter, the smallest division on the meter stick. So take that reading now and write it down. Now we're going to take a look at the reading for the other pole. Okay, here's the pole on the right-hand side. Again, I would recommend that you read from the inner surface of the pole there. Take your reading to the nearest millimeter and write it down. And so the distance you'll be interested in is the difference between those two readings. That will be the distance in meters between the inside surfaces of the uprights. So with that information and the physics that you already know, you should be able to calculate the acceleration two different ways and compare. Next, you'll download the instructions for the laboratory and carry it out. Here we're going to be looking at what a spring scale measures. Now you may think, well, that's pretty simple, it just measures weight. But it's not quite that simple. Let's take a closer look. This scale has a spring built into the plastic housing here. When you put a weight on the scale, the spring stretches, and that causes the needle to deflect and give you a reading in terms of newtons. Now the object that we're going to be weighing is this soda pop bottle that we filled with sand. It has a mass of about 1 kilogram, so its weight should be about 9.8 newtons. And as you can see from the scale reading, it's right around 10 newtons. Now we're going to look at the forces acting on the scale in this situation and go from there. We begin by representing the bottle of sand with a point. There are two forces acting on the bottle. One is the tension force of the scale acting upward. The other is the weight of the bottle of sand acting downward, mg. To set up a net force equation, we need to define a positive direction. Normally that would be in the direction of the acceleration, but in this case the bottle of sand is not accelerating, so we can choose either up or down. I'll choose up for positive. The next step is to write the net force equation. F net equals, now the upward force is T, and that will be positive, so I'll write that first. And the downward force is mg, and that's negative, so that will be subtracted from T. Now since the object, the bottle of sand, is not accelerating, the net force acting on it is 0, and therefore we can say that the tension force is equal to mg, the weight of the bottle. So in this particular case, the spring scale measures the weight of the bottle. So we've seen that to keep the object in equilibrium, I have to exert a force upward that's equal to the object's weight. Now you may have noticed that as I've been holding this, the needle has been oscillating back and forth around 10. So since the needle is reading different things even while I'm holding the same bottle here, there must be something involved other than just the weight of the bottle. That thing has to do with the fact that I can't hold the scale perfectly steady, so I'm exerting small accelerations on it up and down. Let me exaggerate that by pulling the scale up quickly. So I'll give it a quick upward acceleration. You watch what the needle does as soon as I pull. Now at the instant I pulled, you saw the needle go up. Now at some point, when I came to a stop, the needle also came to a stop and came back down again. Let's concentrate first on that first part where I did the upward pull. Let me do it one more time. Okay, now we're going to go back and look at the forces there and do a force analysis for this situation. For this situation, we applied a greater tension force in order to achieve an upward acceleration. The net force equation will look the same as it did before, because we still have a tension force and a weight force. We still have the direction of positive up, and so F net equal T minus mg. What's different is that the net force is no longer 0, because the acceleration is not 0. The net force, by Newton's second law, is the mass of the object times its acceleration. This is equal to the tension force minus the weight. Solving this for the tension force, we get T equal mg plus ma. So we find that the reading of the spring scale, which is the tension force, in this case, is equal to the true weight of the object plus the mass of the object times its acceleration. So what we saw with the force analysis was that the scale reads the tension force. In the case of equilibrium that I have here, that tension force is simply equal to the weight of the object. But when I was accelerating upward, that tension force was equal to the weight of the object, mg, plus the mass of the object times its acceleration, or mg plus ma. We call that the apparent weight of the object. In other words, what the scale measures, the tension force, is the apparent weight. The true weight would be mg.